Hello, in this video I'm going to make a start on electrical circuits. So this means current electricity, the transfer of energy through the movement of electric charge, as opposed to static electricity when we got the electric charge just sitting there, not moving around. Now I'm going to cover a lot of ground in this video because I think with electrical circuits, in my view, it's best to start looking at actual examples rather than get too fixated on theory. But there's still two things that I really want to cover in this. I want to get a basic description of electric current and what's happening in a current carrying wire. Now, this is going to be fairly primitive, but there's a couple of misunderstandings that I just want to make sure that people don't have from the outset. So I'm going to try and get a sort of primitive description of current. And then after that, I'm going to describe the key features of electricity. This is going to have a few formulae thrown in, and this is going to be the basis of how we're going to then analyze circuits that I'm going to put up in subsequent videos. So I'll start off then with this basic picture of what's happening in current then. So if we're going to want some electrical current, we're going to need two things. We need some charged particles, and then we need something to get them moving. So to have some charged particles, that means we're going to need a conductor, as opposed to an insulator. So conductors have got lots of electric charge that is relatively free to move around. This is going to mean really one of two things. The main thing that we're going to be looking at is in metal wires. So a metal has got a lot of, relatively speaking, it's got a lot of free electrons. Electrons that can relatively easily move around inside the metal. So that makes them a good conductor. Or we've got electrolytes, where we're looking at liquids. Usually got something dissolved in them, which is then separated into ions. So we've got charged particles as ions, which might be positively charged, negatively charged, whereas in metal we're talking about negatively charged electrons moving around. But then in electrolytes, we can then have the movement of the ions in a liquid. Now we tend to talk about electrolytes less because they don't come up so much nowadays. Wet cells aren't used as much anymore, so batteries that have got liquid all the way through them, mainly we use dry cells nowadays, or we've got things, if we're just talking about plugging stuff into the mains, of course we don't have electrolytes or cells of any variety plugged into those, so unless we're recharging a battery. So that's where we're getting our charged particles from. Then we need something to get them moving, which is where we come across the term EMF, electromotive force. And you can see where the name comes from, even if it does sound a little antiquated, because we got electro for the electric charge, motive for motion, and force for, pushing something. So we got the force that puts electric charge into motion. So you can see how they came up with the name, even though it's not always helpful nowadays talking about EMF and can sometimes confuse people. But this is our energy in, we're doing some work on some electric charge in order to get it in motion. So we've got a force, so we start thinking about work. So we're doing work on the electric charge. So what's then happening? Let's just think about, let's stick with it in a sort of primitive starting point of, let's just think about doing a push on some electric charge. If we've got a wire and we've got all of these electrons sitting inside the wire, then they might all just be sitting around doing whatever they're doing. Then we have some EMF, some electromotive force, something which is getting charge in motion at one end of the wire. Now, we don't have to push these charges very much. There's loads of them around. They're going to be getting closer then to other charges. These are negative electrons. We're going to be doing work on, say, this first electron in order to get it closer to the second one. We're building up the potential energy. We've got a potential energy increase. And of course, potential energy is a property of a system, as we were saying throughout classical mechanics, rather than just a single entity with its kinetic energy. And we've got very little kinetic energy. This is really low all the way through the current. The electrons aren't moving particularly quickly. So we're really talking about a transfer of potential energy, because as we do work on this first electron, we're going to get it closer to, say, another electron. That's then going to push that one away. We're going to get this chain where the electrons don't have to move very much, but because the interactions here are all in the electric field, and the interactions in the fields, this all happens at the speed of light. So we're going to get this speed of light transfer of potential energy along the wire with very little kinetic energy. So that's what we're really looking at here in a current carrying wire. We're transferring energy as potential energy, electrical potential energy, at the speed of light along the wire, because it's all to do with the interactions of the electromagnetic field. Then when we've got various components inside the circuit, so wires we quite often treat as being ideal, as in we get this 100% transfer of potential energy. There's no losses. Okay, that doesn't actually happen in reality. Wires heat up and we get some energy loss. It's not 100% transmission. But ignoring the wires for the moment, whenever we get a component, so there's two things that can happen when the current is passing through a component. We're going to get some energy is transferred onwards to more, further components down the line in the circuit. So we've got onward transfer of energy in the field, this onward transfer of potential energy. But we've also got that the electrons in their movement are going to do some work on the component, which is then going to have a release of energy from the circuit. So, if this was a bulb, there's going to be some work done in, say, well, if it's a filament bulb, in heating up the filament of the bulb. That is then going to release light and heat from the bulb, and we're taking energy out of the circuit. You still get some more if there are further components down the line. You're still going to have transfer of some more energy along the circuit. So we're going to be thinking about the components in the circuit as well. How much energy is being passed on? How much energy is being taken out? And by thinking of this, this movement of energy in the field and the work done then by the electrons on the component, you can see then why it doesn't really matter if we've got direct current or alternating current, because whichever direction the electron is moving in, whether it's going off to the right or whether it's going off to the left, or whether it's going backwards and forwards because we've got an alternating current, these things are still happening. We've still got an onward transfer at speed of light of potential energy, and we've still got the electrons doing work on the component. So it dispels that illusion that some people have when they first think about circuits, of thinking, oh well, I can understand direct current because we've got some electrons here which are given a whole load of energy, and they whip along to the other end of the circuit and they take their energy with them. Well, that isn't what's happening. We as I say, the electrons are barely moving. They're going at like millimeters per second, something that I'll quantify in another video when we look at the drift velocity. But they're barely moving. Okay, they are doing some work on the components, which is then going to release some energy, but it's the field which is transferring the energy. So it doesn't matter whether the electron is moving a little bit to the right or a little bit to the left. We're still getting this rapid speed of light transfer of electrical potential energy through the components of the circuit. So that's probably all. I think that's all I'm going to say about building up a picture at the moment. We might get more as we work through examples and such like. But it's just this primitive understanding of what's happening in terms of the energy in an electrical circuit. So what terminology are we going to use to describe all of this? Well, there's a handful of key terms that they're relatively simple, but quite often people get slack in actually really understanding what they mean. So we've got this movement of electric charge. So we can start by talking about current. This is our rate of flow of electric charge through a point in the circuit. This is what we're measuring in amps. This is our rate of flow of charge through a point in the circuit. We can say then that, well, that must be coulombs per second. We measure charge in coulombs. We've already spoken about that in structure of matter. So this is coulombs per second. Current, which we usually denote with an I, we can then say, well, it's the amount of charge in an amount of time passing through a point in the circuit. So, excuse me, so that's our electrical current, the way that we're going to describe that. We're talking about energy all the way through this. So we want to talk about, first of all, potential. So this is our electrical potential. This is our energy per unit charge. So for each bit of charge that we've got moving through the circuit, how much energy is that actually carrying with us? So this is, again, at a point in the circuit. We're measuring this in volts. This is our joules per coulomb. So a very, very important definition that a lot of people, when they're beginning on electricity, don't really spend enough time getting familiar with. So we've got, that's our potential. So this is the energy per unit charge at a particular point in the circuit, which allows us then to look at potential differences, because this is going to then allow us to say, well, how much energy is getting used in a component in the circuit, or even how much is being put in as well. We can consider the EMF. I've said here it's energy in. We can consider this to be a positive potential difference because energy is coming in. And for a component, like when I was looking at this bulb over here, this will be a negative potential difference because we're taking energy out. So a potential difference is just saying, well, what is the difference in potential between 2 points in the circuit? Usually we're going to look on either side of a component in the circuit and then say, well, what's the difference on either side of that? So it tells us something about how much energy is being used. Again, we're still measuring this in volts because it's a difference in potential, and potential is measured in volts. So that's what we have with potential difference. We want to talk about power, our rate of transfer of energy. So usually we'll talk about the power of a particular component, whether it's the power of the energy coming in supplied by our power source, or whether it's the energy that's going out in a bulb. We talk about 60-watt light bulbs and things like that. So the power of the component, this is equal to the current times the voltage. And we can just see this from the definitions, that if we've got current is coulombs per second and our voltage is joules per coulomb, when we multiply those together, that is going to give us joules per second, which is our power, which is our watts. So simple way of working out power. Again, I'm whipping through these because I'll be able to give actual examples of these in a moment when I draw up a very basic circuit. The other thing that we talk about, of course, is resistance of a particular component. We can think of resistance in a couple of different ways. So we could say that it's the opposition to the flow of current, or we could say that it's some measure of the energy required to pass a current through that component. So we've got that the current is equal to the potential difference divided by the resistance for a particular component. So the current through the component is the potential difference across the component divided by the resistance. So as resistance goes up, current goes down. So it fits with that idea, as I say, of resistance being the opposition to the flow of current. R goes up, I goes down. We can also say that the voltage, so our potential difference across the component, is proportional to the resistance. So when we've got a circuit of a whole load of different components, the total potential is going to be divided up in proportion to the resistance, because the resistance is telling us how much energy is going to be used. And again, this is something that I'm going to come to in a moment in an actual example, just to clear that one up. This does touch actually on, as last thing I'll mention on this slide, with Ohm's law. So you can see we've got something, we're sort of skirting around it with these two expressions here. So Ohm's law, this was, what was his, I think George Ohm? So we're going back it's around about 200 years. I think we're just coming up to 200 years since Ohm's law was set up. And this was Ohm was saying that the current, he saw that the current was proportional to the potential difference through a particular component. So, and this is true for any component. And then he was saying, well, the constant of proportionality is then resistance of the component. Now, for Ohm's law to be true, he was talking about particular materials where this constant of proportionality is actually a constant of proportionality. You know, I know that's just saying that it is what it is, but you've got, if we're going to say, well, V equals IR, which is the usual equation that people are familiar with, well, this is only representing Ohm's law if R remains a constant. So whatever voltage and current combination we've got is got the same resistance. Now this isn't always the case. You know, we've a lot of components, the resistance is going to change depending on circumstance. Yeah, you've only got an ohmic conductor, something which is obeying Ohm's law, if we've got this constant resistance. We've got this proportionality, as in if you plotted out a graph of our current against the potential difference, that we're going to get this straight line. Now, not all components have that proportionality. That means it's obeying Ohm's law, but you'll get other ones where, you know, it might vary, something like that, in which case it's not obeying Ohm's law. That doesn't mean to say that V equals IR doesn't apply. That still applies, because that isn't actually what Ohm's law is. You know, this applies to all components, but you've just got the resistance changing because it's not a straight proportionality. So yeah, it's just being clear about exactly what Ohm's law is in that particular case. So we can still use that V equals IR, you know, that's bringing us on. Well, we've got two of our big equations here. We've got the power is equal to the current times the potential difference. And then we've got this V equals IR. Of course, we can combine these into a whole load of different forms. You know, we can say that power is current times voltage, but that's also going to be the square of the voltage divided by the resistance, and is also going to be the square of the current multiplied by the resistance. That's just, you know, riffing on those and getting the three different permutations. Right, so what happens then, let's put this into an actual circuit, and then some of this will make a little bit more sense. Let's do something really basic then. We'll just have a cell where, so you've got the positive terminal is a long line, the negative terminal is a short line. Sometimes the negative one's drawn a bit thicker than the other one. Then I'll just stick a few components in. Let's do a resistor. We'll just make it a really simple series circuit. A resistor, a bulb, and then another resistor. It doesn't really matter for what I'm going to do, what I've put in here. Let's say, to make it simple, that this is a 10-volt cell. So that's our EMF. So that means that the potential difference across this cell is going to be 10 volts. I'll get onto that in a minute. Let's stick some resistances down. So say 2 ohms, 2 ohms. No, actually, let's make that 1 ohm. Make it a bit different. So we've got 2 ohms, 1 ohm. Actually, I'll make this one 2 ohms. I could have left it as it was. But anyway, I just want to make them easy numbers to not get too fiddly on the maths. Right, so say we've got this set up and we just wanted to know, well, what's actually happening all the way around here. Let's start with potential then. So remember, we had that difference between potential and then potential difference. So for conventional current, we're going from positive to negative. Now, I know, you know, electrons are going to be going from negative to positive. So the actual flow, this is direct current. The actual flow is going to be going clockwise. But conventional current, because they drew the arrow in before they knew anything about electrons, you know, remember all this stuff started in the sort of early to mid 19th century, where they didn't discover the electrons till the end of the 19th century. So they had no idea that everything was actually going clockwise. They drew the arrow going from positive to negative. So that's conventional current. We can mark on points of potential. So, you know, potential, much like gravitational potential, you can set your zero wherever you want for the purposes of this, because we're going to look at potential differences. And if we're just looking at differences, it doesn't matter what the absolute numbers are. So if we got a 10-volt cell here, let's say, well, we start off as we go in, you know, there's no loss in these wires. We got 10 volts there. We're going to end up with no volts when we get to the end. So we can already see our potential difference across the cell as we go across it there. We're going plus 10. Now, all of these other ones here, okay, now EMF that we've got here is positive, but all of these components here are taking energy out of the circuit. They're going to have negative potential differences. So, and the potential all the way round is going to be divided up in proportion to the resistances. So we've got 10 volts to divide up over a total resistance of 5. So each 1 ohm is going to take 2 volts. So we're going to have 2 volts across this, we're going to have 4 volts across that, and we're going to have 4 volts across that. So this 10 volt here, which is the potential at that point, we're going to get a loss of 4 volts down to 6 here. So this is showing the difference between potential, our 10 volts, our 6 volts, and our potential difference, the 4 volts, the difference between the two of them. Another 2 volts here across this one, which is then going to bring us down to 4, and then the remaining 4 is across this resistor at the top. So you can see then the difference between potential and potential difference. And this is just showing the amount of energy which is being taken out in each component. But of course, the rate that is coming out depends on how quickly we're pushing the charge through. You know, the voltage here, we're talking about joules per coulomb. Well, how much coulomb are we getting? How many coulombs per second are we getting? This is where we need to go to the current. So we can look at the current in this circuit and say, right, well, going through each component, you know, we've got our V equals IR, or more to the point, we want the current here. So we've got V over R. So for each component, you look at the potential difference. We've got 4 volts divided by the resistance. So we've got 2 amps, 2 amps, and 2 amps. So we've got the same current because we just got a series circuit. I'll get onto that in a little bit when we look at Kirchhoff's laws. But we got the same current all the way around. We could have said, actually, let's look at the circuit as a whole. Say, well, the current going in and out of the cell is, we've got an EMF there of 10. Total resistance of the circuit is 5. So once again, we get our 2 amps. Lots of different ways to skin a cat there. So that's telling us how quickly we're pushing the charge through all the components. We've got the voltage telling us how much energy is associated with each unit of charge. So then we can get our power being the I times V, or any of the others, the V squared divided by R, or I squared multiplied by R. So we can go through each one of these components and see the rate of energy transfer out of the circuit. So in this case, we've got 8 watts, 2 times 4. Here we've got 2 times 2, so we've got 4 watts coming out of this one, and then we're going to have another 8 watts coming out of the top. So yeah, we've just got that that simple way of multiplying these things together. And again, we'll see that the total wattage, where we add well, 8 and 4 gives us 20, which is the same as 10 times 2. So it's just working through these basic permutations on all of these circuits. Right, so what have I got left to talk about on this? Well, actually, let's say one thing about resistance here. Now, I'm going to go into all components, or the main components, into greater detail in another video. But in terms of just dealing with a single material and resistance, so for a particular material, we start with resistivity, which is given this a rho symbol for, you know, the Greek R for resistivity. And that's sort of our abstracted material related measure of resistance for a particular material. So it's taking the shape of the material out of any measure of the resistance. because if you turn a material into, say, a wire, then the longer the wire, the greater the resistance, and the narrower the wire, the greater the resistance. And this kind of makes sense, doesn't it? You know, if you've got a short, thick wire, you've got very little, you've got loads of charge carriers which can easily move around. They're not being compressed into a small space, and you're not having to go very far. So you're going to get fewer losses. So when you then create, you shape your metal into a long wire, well, the resistance of that wire is going to be the resistivity multiplied by the length and then divided by the cross-sectional area. So as you get a thinner wire, resistance goes up. As you get a longer wire, resistance goes up. Now, the actual resistance of components in the circuit are going to depend a lot more than just a simple calculation as that. And I'll go into that in more detail in another video. But as a basic starting point of just manipulating a single material, then we've got some calculation there. We've also got Kirchhoff's laws, which I mentioned in passing when we were doing this sort of basic circuit analysis. So Kirchhoff, he's got these two laws just describing how current and potential difference behaves around a circuit. So we've got the first one, which is to do with conservation of charge. And that is then just saying that if you then get branches in a circuit, that the current going into the junction is equal to the current going out of the junction. So if we've got a wire which then splits, if you've got current I coming in and then I1 and I2 going out, then we've got our junction there. So I is going to be equal to I1 plus I2. And this is just really saying that, charge is conserved as we're going through these junctions. We've got a rate that charge is coming in. That's going to be the same as the rate of the charge that's going out. So that's one Kirchhoff's law. And the second one is to do with energy conservation, where he's just talking about the adding up the potential differences. We've got closed loops in these circuits, and we need to balance the books when it comes to energy. So our EMF is going to be equal to the sum of the potential differences around the closed loop on the circuit. So whatever path that we actually take around the circuit, it always has to add up that the amount of energy that comes in is the amount of energy that goes out. So our EMF is equal to the sum of the potential differences. So that's the two Kirchhoff's laws. And this is useful for them when we put together how to add up resistors. This is the last thing that I want to talk about. So if we've got these resistors arranged, and when I'm saying resistors, I'm talking really about any electrical component because they're going to have resistance. How do we combine resistances? What if we've got a really complicated circuit, where it's not just in series? We're starting to break this up into various chunks. It's a lot easier to analyze a circuit if you can combine these in some way, because we've now got multiple paths going around the circuit. Things start getting more complicated. So adding up resistors in series. So if you've just got, I'm going to leave this space here for doing stuff in parallel. So I'm going to squeeze the series one in, say here. So say you just started off with one resistor R, you've got a current I, we've got our potential difference across it V. So we already know that R is equal to V over I. That's just rearranging our V equals IR. So what if we've now got two in series? So we've got an R1 and R2 with potential difference V1 and V2. So we know from Kirchhoff's first law that we've just got the same current that's going to be running all the way through this. So what's happening now with all of this? Well, we can say the total resistance, let's write it down here, our total resistance is going to be equal to the sum of those potential differences, that's coming from Kirchhoff's second law, divided by the current. That's going to be equal to I times R1 plus I times R2 divided by the current. And then we can cancel all the I's. So the total resistance is just adding them up. So that's the simple bit that I'm sure you're familiar with anyway, of how we just add up these series resistors in order to get the total resistance. And it's a consequence of just applying Kirchhoff's laws. That we've got that same current that's running all the way through it because of Kirchhoff's first law, and we've got this, we can add up these potential differences because of Kirchhoff's second law. Right, if we've then got a parallel pair of resistors, we're just doing the same thing, applying the same rules. So now we've got the current is coming in and splitting into an I1 and an I2. We've got an R1 and an R2 on the resistors, but now we've got the same potential difference across both of the resistors because of Kirchhoff's second law. Once again, whichever route we're taking, we still must be using the same amount of energy because we need to satisfy our Kirchhoff's second law. So now when we're working out total resistance, we're going to say that R is equal to V over I1 plus I2. So similar to what we had here, but it's now the current that's changing rather than the potential difference. We can rewrite that as V over R1 plus V over R2, cancel all of the V's, and then you get that formula for parallel resistances, which is the one with all the reciprocals in. So 1 over the reciprocal of 1 over R1 plus 1 over R2. Now, of course, you can extend both of these cases to have multiple resistors. You're just going to be adding more in, an R3, R4, R5. Just keep adding those on to the end. So we'd have for series, we just keep adding them up, and for parallel, we'll keep adding on those reciprocals. So those resistance rules, which we'll be using time and time again in our circuit analysis, it just drops out from Kirchhoff's laws. One thing I'll say about the parallel resistances, and I'm really beginning to run out of space here, is get used to situations that just come up time and time and time again. Like if you've got two identical resistors in parallel, we can then see that we're going to have, okay, well, let's stick it into that formula. We've got the reciprocal of, 1 over 1 plus 1 over 1. So the reciprocal of 2 gives us a half. Right, so when they're in a 1-to-1 ratio, that leads us to a half. If you've then got a, so say we add 2 ohms on one side and 1 ohm on the other side, and then you put it into this. So we're going to have a 1 over 2 plus a 1 over 1. So that's 3 over 2 reciprocal. So if they're in ratio of 1 to 2, then we get 2/3. If you keep doing this and you have these 1 to 3, 1 to 4, 1 to 5 ratios, then all we're doing is extending this sequence 1, 2, 3, 4, 5, 2, 3, 4, 5, 6. So these ones come up quite a lot. So it saves you having to go to the formula all the time in order to work out parallel resistors. If they're in just a straight multiple, you've just got this basic ratio 1 to 1, 1 to 2, 1 to 3, and you can just put it in straight away and say, well, what the combination is be. So if we've got 4 ohms and we've got 1 ohm, then we can say, right, well, the total resistance of this, we've got a 1 to 4 ratio. The total resistance is going to be 4/5 of the lower resistor. So we've got 4/5 of an ohm. That is going to be our total resistance. Because this makes sense, doesn't it? If you've got resistors in parallel, you're giving more opportunity for the current to flow. So you must be dropping the overall resistance when you're putting these in parallel. It's got to be less than just having the 1 ohm resistor on its own, because we've now got another option. Okay, it's a difficult path to get through, but it's still another option. You're widening the path to some extent. So when you're putting these resistors in parallel, you're reducing the overall resistance. If you're putting them in series, well, you're just increasing the overall resistance because you force them through one thing. Well, now you've got to force them through another one. It's just even more obstruction to the flow of current. So we'll be seeing all these in a lot more, detail and in more examples, actually as I go through, which is what I'm going to be doing in the next sort of 5 or 6 videos. I'm going to go through a range of circuits and just apply all of these things that I've gone through pretty quickly here, because it just makes so much more sense when you're actually looking at specific circuits. Right, so as I say, I've covered a lot of ground there. I don't really want to say any more. That's probably covered about 90% of the content that you'll have on circuits. I don't think there's going to be that much left. So squeezed it all into this one video, and we'll just unpick it all as we go through example circuits coming up now.